All right, so we'll get going. This webinar here, it's going to be focused mainly on two things with regard to Silego products. We're going to talk about our packed chips, which are mixed signal, configurable mixed signal ICs, and we're going to talk about our load switches and our kind of our really advanced MOSFET kind of things. They work both hand in hand and work perfectly for this type of application for supercapacitors. A lot of the techniques you're going to hear with the supercapacitors can also be used in a whole host of different areas, but we'll be applying obviously these techniques to supercapacitor, but by no means is this seminar exclusively limited to supercapacitors and what can be done with them. But nonetheless, it's useful for all different types of things. Okay, we're going to go ahead and get started. Now, one of the things we try to do at Silego in these seminars is we try to link all of our comments back to either application notes or example projects or white papers, this type of thing that have been written, so you can go and dig a lot deeper. There's only so much content, obviously, I can give in an hour-long seminar with 30 plus types of slides. I can't make you an expert in supercaps, but there's a whole bunch more information that will follow on if you check out our website, that you can dig into it in a lot more detail. In addition, we're going to have a couple of more supercap seminars coming out in October and November of this year, as well as part of a three-part series here. So we look forward to you on that. For some of the content for today's seminar, we're going to look at application note 1195, as well as the reference design by David Rydell for the supercap charging and discharging circuits, and all of those resources are zipped up together. The application note I forgot to mention is by Ramkumar Ramaswamy out of India, and he writes a bunch of our application notes for us and does a really great job at that. We're very thankful to have him as one of our writers. Now, let's first talk about technology so we can kind of orient ourselves about what we're going to talk about with respect to supercaps. First of all, Silego products are really, really small, so they're perfect for IoT applications where size matters a lot. We have some of the world's highest efficiency MOSFET, load switch kinds of things, and so our devices are very, very good for switching power. So you think small sizes, switching power, that's like perfect for IoT applications. And now we look at IoT applications and we say, what matters in terms of the features and performance they would expect? Well, for starters, a lot of IoT applications are mobile. They're always on. They're constantly monitoring, constantly sending data and whatnot. Very often, because they're mobile, they're not hooked to line power. They have to have batteries or supercaps or otherwise, or energy harvesting, these types of things. And furthermore, they can't require a lot of maintenance. One of the promises of IoT is that it's a trillion node network. And if you've got a trillion nodes, obviously you can't be spending $100 a node, or that's more than the value of the entire world economy. And likewise, you can't be spending $1 or $2 upgrading and maintaining the maintenance of each node, as that is also prohibitively expensive. So you need renewable energy where you can do energy harvesting or solar power or very, very long battery lives. Most of it's mobile, so you can install it quickly, wireless, so once again, so the installation costs are low. And then low maintenance, simply because you can't afford to maintain systems with tons of nodes that are expensive. So the supercap overview in particular, there's a lot of great companies in the supercap business. You've got Murata on one hand, Maxwell on another. There's just a few pictured here. There's a little bit of CapEx down here as well. And we're using all of their imagery here. And so definitely check out their websites. We've got links to them. And supercaps have come a long, long way since even just in the past 5 years. The energy densities have improved, the performance has improved, the quality's improved, the cost structure's come down. Lots and lots of really solid improvements in the supercap world, and so the volumes have been increasing as a result. That number of applications they can successfully play in is going up as well. Now, supercaps, where do they fit in the whole battery, the whole energy storage? So you got batteries on one end, you got classical capacitors on the other, and then supercaps are kind of in between that. And we'll talk more about exactly where they fit in a moment. Generally speaking, one of the things we're going to keep in mind about supercaps is they're really, really good at fast energy storage and fast discharge. And so let's talk about a few applications where that means. You might think like in an automobile, regenerative braking. So as soon as you hit that brake, there's a tremendous amount of energy to be stored. Well, we all know that if you look at a lithium-ion battery, it doesn't charge very fast. It can take 3 hours for a full charge. Well, it can't capture all of that energy, but a supercap actually can capture that energy and store it. You think about like a hotel door lock. If you want to do energy harvesting, the twist of the door handle itself produces a really good amount of energy. I mean, we're talking like momentarily a watt or a half a watt in a doorknob turn, but it happens very quickly. And so where are you going to store that energy? You can't start to charge a lithium ion and grab that energy, so you'll use a supercap. There's a lot of other cases where supercaps are used, like in water meters, where you can take the energy off of a very, very high density battery with a very high internal impedance, where you can't draw much current off of it, but it still has a very high level of energy density. You can draw that energy off, you can pump that over to a supercap, store that energy in the supercap, and then when you turn your RF on, you can dump a lot of current and get a very, very long distance transmission with RF using a lot of energy quickly, which you can never get out of the batteries. So they can use as buffering applications like that. And finally, they're actually being used in even really large applications where you might have a windmill or you might have a power station. It's almost like a decoupling cap for the entire power station. And you could think that, once again, in a classical battery, it just takes too long to put the power in and take too long to get the power out. And in these kind of applications, because the energy density as a function of volume, the volume density, isn't very good with supercaps as compared to batteries. But if you're in a huge industrial setting, generally, the kind of storage spaces and whatnot are easily available. And so supercaps are an ideal situation for those types of applications. All right, now let's talk about how a supercap actually stores charge. So first of all, we all know a capacitor. It's the classic one you learned about in physics class, where you've got two metal plates and something separating them. If you have air separating, the dielectric constant is 1. That's what we show on our little formula here as the little e. And you've got the area, the size of the electrode, and then you have the spacing, how close the electrodes are to each other. And you multiply the area times the dielectric constant, you divided that by the separation, and you'll come up with how much capacitance is in a capacitor. Really, really traditional. Nothing really new there. Now let's talk about the supercap. So the way it works is also quite similar in that it has 2 electrodes, nothing new there. But instead of having like a separating dielectric constant, it has an electrolyte. Think about it as a fluid with some carbon atoms in it, and that fluid goes in there as an electrolyte, and because it's fluidic, it has a tendency and there are charged particles in there. When you put a charge on the various electrodes, there's just a tiny little bit of separation that happens, and because the activated carbon cannot pass the electricity, it's able to store that charge, and you can see it kind of working like that. And what the beauty of it is it allows the 2 electrodes, because you have these little carbon atoms, it allows you to put the electrodes incredibly close to each other. In most cases, like a traditional cap, you can actually see the gap. The gap is, in a classical, 1 1 microfarad type of cap, you could even see a gap of 1 millimeter or so. Well, in this case, the gap can be as low as 0.3 nanometers, you know, and as high as maybe 0.8 nanometers. I mean, we're talking on the terms of 3 angstroms. I mean, we're talking on an atomic level is the closeness here. It's really an impressive technology from that standpoint. And yet, even though it's so close, you would think that it's a dielectric breakdown would, you know, be incredible. I mean, you'd think it'd be in the millivolts, but it's not. They can get dielectric breakdowns, you know, up at the 3.7, 3.8, 3.9 type of volts, where you can overstress them up to that point. Actually, they start leaking, and you can actually go quite a bit higher than that. But nonetheless, that we'll talk about that in a minute. So, where do the supercaps fit in terms of energy density? Well, they're certainly a lot better than classical capacitors, but they tend to be anywhere from, 5 times less than a lithium-ion battery, sometimes 10 times less. In the volumetric size, you know, what is the size versus the energy density? They're not nearly as good as batteries in that case. But then here's the impressive part, the charge time and discharge time. They're much, much, much better than batteries. And in fact, they can charge so fast or discharge so fast that you really have to think about the MOSFETs that you're using or the load switches that you're using, because if you take like a 1 farad supercap and you turn on, you know, you take a power supply and you take a really good FET and you just turn it on and go to charge that supercap's impedance can be as low as, you know, a few milliohms, and in which case you're going to get, you know, 10, 20, 30 amps of current come flying out of, being sourced into the supercap, and your power supply might not even be able to supply that kind of power, in which case you're going to brown out your power supply, you get all kinds of problems, you reset your circuit and you have a big mess. So supercaps really need to be thought about in terms of how you design with them. How do you limit the current? How do you charge them? How do you do active cell balancing? How do you worry about the temperature? And a lot of these things. We love those kinds of problems because that's what Slego can very easily and cheaply solve. Now, let's continue down the list here. Cycle life. Supercaps are phenomenal. You know, they can be charged and recharged over, you know, 1 million times in many, many cases. I mean, it's just incredible. So you don't have the traditional 2,000, 3,000 life cycles of a classical lithium ion. And finally, there's all different types of solutions that can run the gamut from all the way from the capacitor to a battery. Murata has some offerings out there that allow batteries and supercaps to go together. Obviously, you could use a plain old battery and a supercap independently and build your own control circuit or however you want to do it. All of these are viable options. Slego doesn't really have a dog in this hunt in the sense of, you know, I'm not trying to guide somebody to a supercap. They're very different than batteries. They have some very good uses. I'll give you another great use in the IoT world. Let's say you have a pen. It's a Bluetooth attached pen. Rather than put a battery in it, you can put a supercap in it. You just simply touch a charging pad. In a matter of 1 second, your whole pen is charged up. It'll work for a couple of hours, and you charge it again. You don't have to wait for a lithium-ion battery to charge up for 30 minutes to an hour or even 2 hours while before you can start writing again. Supercaps are wonderful for those kinds of applications. And then you've got the mixture once again between supercaps and batteries and all that kind of thing. So we don't care. We've got solutions for lithium ions. We got solutions for supercaps. We've got solutions for a mixture between supercaps and batteries and plain old capacitors and energy harvesting devices and you name it. Generally, you can configure a pack or one of our load switches into being a useful part of that control circuit, and do that very small and very cheaply. Okay, so let's talk about some of the problems that we need to go solve when we think about incorporating a supercap into our system. The first thing, obviously, is we've got to get power into the supercap, and we've got to get power out of the supercap, so charging and discharging. Then if we use multiple supercaps, there's something called cell balancing. We'll describe what that is, and we'll go over that. And then the next thing is, in order to get maximum use out of your supercap, you want to use all the energy into that. And how do you do that and still maintain a fixed output voltage And there's other variations of that. For example, how do you take a variable input voltage and be able to charge a supercap? There's all different kinds of things to think about on that side. And then we have what happens when supercaps go bad, when they get old, they get too hot, the electrolyte dries up. How can we detect a bad supercap? So we've got some circuits on how to do that. And then there's something called ripple current monitoring. Basically, this is the self-heating of the supercap. When you take current and you put it in and out of the supercap quite rapidly, because you can put amps and amps of current into these supercaps and out of them. And even when a supercap only has a few milliohms of impedance, that still can heat up, and that can limit the age. So you might want to the lifespan of the product, it can limit. And so you probably want to be able to monitor exactly how much ripple current and things like that's going on. This is high frequency currents, things like that. And then also, just plain old ambient temperature, being able to monitor that. And finally, we'll go into some interesting things like what happens with reverse voltage, what happens with overcharging, short circuit protection, and how can we use our chips to prevent reverse voltage, prevent overcharging, and monitor short circuit protection. Okay, now I'm going to slow down here for just a moment. And has anybody got any questions? Okay, one of the things I was thinking about was, let's see. Yeah, I don't see it here. Actually, Tranger Sydney, if you're online, can you send me that video link again? I failed to pick it off before I started the seminar here, so I need to get that again if you can do that. All right. Okay, I'm gonna keep going until I see a link that pops up from one of these, from one of my co-workers. At any rate, okay, so continuing on. So we're going to use the control element in the circuit here is going to be Selego's configurable mixed signal IC, and I think I'm getting it. Yeah, okay, I got it. Yeah, we're going to use Selego's configurable mixed signal IC as the control element, and then in some cases our CMICs actually have the power MOSFETs integrated, and so the power paths will be inside our device. And then at other times, we'll go ahead and use some of our load switches and whatnot to do the current inrush limiting and those kinds of things within this. And so it's a combination of our configurable mixed signal ICs, and all of this is available on the website. You can look it under GreenPack. Software is available, all this type of thing. And what's another thing that's beautiful about this particular program is these chips come undefined. So if you've always had a passion to be a chip designer, you actually can get one of these blank mixed signal ICs, go put in your circuits much in the same way that you maybe did in the university when you got your white patch board, you put all your parts down the middle and then you used wires and you connected it all together. You can do the exact same thing with our configurable mixed signal ICs. Build your own circuit, but instead of having a huge circuit when you're done, you actually have your own IC that you can program in the board itself. Oh, okay. I didn't know the video was going on in the background. So, okay. Now, one of the things I'm going to do, I'm going to go ahead and play a little bit of this YouTube video. I'm going to try to do a new share. Bing.
Hi everybody, Patrick here from EngineeringShock.com and ElectronicLessons.com.
Okay.
I'm not going to show you any circuit today. I'm a bit bored, and so what I'm going to do is I'm going to blow up a supercapacitor. Never done it before, and I'm curious. So I've got a 2.7 volt, 4.7 farad supercapacitor here, and I've got a power supply set to supply 20 volts at a fixed 2 amps. So what will happen is, as soon as I turn the power on, the voltage supplied by the power supply will dip down to 0 volts and slowly charge it up. And I'm going to show you the the voltmeter in the background on my power supply, so you can watch the voltage grow. Now, once the voltage exceeds 2.7 volts in the capacitor, we enter the danger zone. So actually, what I'm going to do is I'm going to focus the camera, turn on the power supply, and I'm going to get the hell out of the room. So let's set it up. So the background's a bit blurry, but when I turn this on, you'll see this slowly rise. And once the voltage gets to about here, we're going to hit the danger zone. So as you can see, I've got my capacitor right here. I'm going to grab my coffee, and I'm going to get out of the room. So now let me turn on the power, and I'm going to run. So hopefully this is pretty cool, and hopefully we get a good explosion out of it.
And here we go. I love this kind of stuff. So, and this is really impressive. So, in terms of.
Okay, well, that was a bit disappointing. It looks like it did pop, but that certainly sucked. I will note that the capacitor itself is insanely hot. Touching it for more than a split second burns.
Okay, so. Yeah, I wanted to show you that it's really impressive, and a lot of good can come out of checking out the overstressing of a particular part. Hold on here, I'm always okay. So that was what happens when you over voltage. I mean, it's really impressive that you can take so much energy there, and the only thing that happened in that particular case was the electrolyte fluid appears like it finally expanded and popped the top off, and then the thing pretty much stopped at that point and didn't even cause a fire or blow up or anything like that, even given the amount of energy density. So that's actually pretty impressive, and hats off to the manufacturer of that particular supercap. But what it did tell you is if you over current or over voltage a supercap, they do get hot and you do damage them. Obviously, that was an extreme test. It's probably not practical, but nonetheless, it doesn't matter. The whole point is you got to adhere to the ratings on the data sheets for the supercaps if you want to have the best, longest life types of products. And over voltage and over current is a problem. So there's a number of different types of applications that you might want to consider, and ICs that you consider in terms of how you prevent this. So there are some dedicated IC solutions that do this, dedicated, or you can use our chip. And so here's an example of one of our chips being used as both a charging and discharging type of circuit. And so this particular chip has been set up with a charge enable on pin 2. That's right here. And this circuit, this schematic that you see here, it's a schematic that is taken directly from the GreenPack Designer software. And this particular product has all of our configurable mixed signal elements in it, plus it has 2 power PFET switches already integrated into the same package. So this is an incredibly small design, only about 2 by I think 3.5 square millimeters is this entire chip. And yet these are very, very high efficiency PFET switches, so they work extremely well in regards to that. And so what this chip is doing is it's monitoring the VN, and it's monitoring the VCAP, and it's controlling the charge switches accordingly. The other nice benefit you get here is if you do have a microcontroller in the system, you can communicate with I2C, and you could come in and change the parameters of this chip, or go and monitor various internal nodes in the chip at your heart's content. There's a lot of things that you can do that we don't have time to talk about today. But nonetheless, this is a basic, super simple, super compact way to do the charging and discharging of the CMIC, of a supercap with our CMIC chip. And you do get inrush current limit, because a lot of these PFET power switches are already set up to have particular slew rates, and you can adjust those slew rates. You can BWM the slew rates. There's all different kinds of control in terms of not dumping too much current onto a supercap too quickly and then running into power supply problems and whatnot. All of that kind of thing can go on with this simple type of circuit. Now let's talk about active cell balancing. Cell balancing is kind of a little bit of a tricky concept. If you have two supercaps and they're identical in value, and let's say they're set up, we're doing a rated voltage here on this screen of 2.75 volts. Now, if you put on a voltage of 5.5 volts, you would expect if those two cells are perfectly identical and you ramp a voltage onto them on the top part of the cells after they're already discharged to zero, and suddenly you put 5 volts on it, those supercaps are going to ramp up, and if they're identical values, if you probe the connection in the series connection between the two supercaps, you will get exactly half the voltage of the total voltage charging the two supercaps. So if it's 5 volts, you get 2.5. It's 5.5, you're going to get 2.75 as the center voltage. Now, what happens though, supercaps are not built perfectly. A lot of them come with plus or minus 20% tolerance budgets. So you can have a supercap that you think you're buying at 1 farad and you're actually, it's a 1.2, and you think you buy another one at 1 and it can be 0.8 farads. And then you stick the two together. Now it turns into the voltage divider of the 1.2 by the 0.8. And so you actually end up with a higher voltage in between, and that higher voltage can be more than 2.75 volts, which exceeds the rated voltage of that lower, that 0.8 farad cap. That's a big problem, because now you're out of spec. And you bought all the parts in spec, you applied the right voltage in spec, but because of the tolerance of the supercaps themselves, you're now out of spec in the middle of the two supercaps, in the middle of where you're probing at the series connections between the two supercaps. And so what you have to do is a number of things. One is you got to do what we call cell balancing, and there's passive cell balancing and active cell balancing. A passive cell balancing would be something as simple as, oh, I'm going to take two resistors and I'm going to make a series connection, and I'm going to make the middle value of the series resistor equal 2.75, and I'm going to put that and connect that directly to the supercap. So now you have two supercaps in series, you have two resistors in series, and those are all connected in parallel. And so if the center voltage starts to deviate too far away from 2.75, it will either source more current in there from the top part of the rail, or it will sink more current out of it for the bottom part of the rail. That's a way to do it. It's just a terribly inefficient way to do it, and it also has a problem of self-discharging, and it balances the cells quite slowly. Not saying in a couple of applications you can't do it, but in most applications they do active cell balancing because it's lower power, it's much faster way to do it. And active cell balancing just takes that whole thing and says, instead of using resistors, I'm going to sense what the voltage is, and then I'm going to switch a switch, and I'm going to really dump current into that node very, very quickly. To balance it up, and then as soon as it's achieved its balance, I'll probably turn the switch back off, but I'll continue to monitor that point with a very low current op amp or comparator to make sure that it stays within the voltage range of the supercaps. I hope that makes sense. So let's take a look at it. So active cell balancing generally requires a couple of discrete things. One is you want to make sure that you don't over voltage the whole stack. For example, if you've got two supercaps rated at 2.5, then the highest voltage that you want them to see is 5 volts, in which case you never want to go over 5 volts. In the case that we were showing on there, it was 2.75, so you never want to go over 5.5 for two supercaps. So you want to have over voltage protection control to make sure, for example, when you plug in your wall wart, or you plug in a cable or something from line power, you don't get a sudden voltage surge or something like that that's going to ripple through and expose your supercaps to over voltage conditions that they might not be happy with. And then the next thing you need to do is you need to make sure not only is the whole stack within the right voltage range, but then you need to actively cell balance every one, because you have to make sure every cell itself doesn't exceed the 2.75 or the 2.5, the 2.8 volt maximum. I think even some of the companies now have voltages tolerances that go up to even 3 volts now. I wonder if any supercap guys are in line and could probably correct me on that. But generally speaking, it's somewhere between 2.5 and 3 volts is where the overstress voltage occurs. So once again, you need the whole stack protected, and then you need every cell protected. So over voltage protection control, active cell balancing, they work together. Whole stack, individual cell. Now in this case, what we've got here is we've got a window comparator, and what we're doing is we're sensing through the balance monitor. We're taking that 2.5 volts in this case, because we're doing a 5 volt and we want to keep it within 2.5 volt. We're taking the what it's supposed to be 2.5 volts in, and we're taking that into pin 13, and we're applying that to 2 comparators. And and what's clever about this circuit is we use 2 of our load switches in Q1 and Q2. And so if the voltage is too high, we turn on one. If the voltage is too low, we turn on the other. And because these are current limit, we're not causing a lot of grief throughout our system. We can turn them on kind of nicely, and they ramp up nice, and instead of just some real hard switch where you get ringing effects and all that kind of thing. We can avoid all that by using our parts in Q1 and Q2 shown in the schematic. Now back on the PSOC, the GreenPAK designer diagram, the references, pin 14 and pin 12, they're coming from a series set of resistors off on the schematic, the upper part that you're looking at, off on the right. You'll see a potentiometer and a couple of resistors, and they're setting up 2 different voltages, an 848 and an 818 millivolts. They come in through those pins, they're applied to the comparators, and that is what sets up our window comparator. Now you say, wow, why isn't that at 2.5 volts? And it's the reason why is because we take the 2.5 volts, and our comparators inside the GreenPAK are only good from 0 to 1.2 volts. And so we actually are setting up those comparators in a divide by 3 situation internally in the chip. So just think about, as that VREF comes in, the whole gain of that comparator is 1/3 of a volt. So when 2.5 comes in, it's cut by 1/3, and if you look at that, it's just over 800 millivolts. So it's very close in there. So the 2.5 volts resides between the 8.18 and the 8.48, and that becomes your window comparator of either charging it more or discharging it, but it will keep everything at 2.5 volts. I hope that technique makes sense. This type of technique to keep a voltage, whether it's a supercap or any other thing, if you want to keep a voltage at a particular rail, is a beautiful circuit to be able to do that. And GreenPAK is nice, and I think in this case we're using our 5th generation series, and there's also I2C, and you can get more information upon this on our website. Now let's take, how do you maintain a fixed output voltage? Now this is important because supercaps obviously aren't the cheapest things in the world, neither are batteries, so I'm not trying to make a comment there, but if you're going to spend a lot of money on an energy storage device, you want to get the maximum energy out of that. So if you're going to charge a supercap, let's say up to 2.5 volts, to produce a 1.5 volt rail, wouldn't you like to use all of the energy from 2.5 volt where the supercap is charged down to the rail, 1.5, but wouldn't you like to continue to use all that energy from 1.5 volts on the supercap all the way until it's down near rail for your fixed output voltage? Well, one of the ways to do that is to use a buck converter or a buck boost converter. So if you have a buck boost converter, then you can use almost all the energy in the supercap to produce a fixed output voltage. Now, this is a little bit different than batteries, and the reason why is because a battery usually maintains a particular voltage for the majority of the lifetime of the battery. So it's only when batteries start to get down in the last 5–10% of their total energy storage do they really start to drop off in voltage. Most of the time they're in 80–90% of their life they're in a very flat region, and so using a nice buck and only is off a buck DC to DC converter to produce whatever rail we want works quite nicely. And many customers, in fact, just ignore the last 5% of a lithium-ion battery life because they don't want to deal with the discharge voltage at that level. But you really can't do that with supercaps. You need to think about the entire history of the supercap, because as you're using the current off of that, it's just linearly decreasing. You know, there's not some happy state. It's just like a capacitor in that regards. If you take the energy out, the voltage drops. And so if you're going to generate V out, let's say V out, let's say we got 2 supercaps and they're charged up to 5 volts, and we want to produce a 3.3 volt rail. You're going to have a buck mode DC to DC converter to drop it from 5 volts to the 3.3 volts. And then you're going to want to have a boost mode. So you're going to have a buck boost converter, and the boost mode is going to pump up the voltage after the supercap has already dropped below 3.3 volts to continue to generate the V out of the 3.3 volts. And in this manner, you can buy a smaller supercap. They're a little more cost effective, and you can generate a lot more power to your end customer with less recharge cycles. So here's an example of how you would do that. This is both a buck and a boost. We've got the buck converter down here, and we have a boost converter up on the schematic here. It's very, very simple circuit in terms of how we produce the buck part of our converters in order to do that. So if you're only bucking, you only need a little tiny green pack and a couple of external FETs or whatnot. And if you're going to boost, well, we recommend that you buy a boost converter. One of these days, we'll get this all wrapped up into a pack chip, but right now it's still a little bit discrete. The next function we want to talk about is we're going to talk about how you detect aging and electrolyte dry up. You can imagine, because there's, you know, the electrolyte is somewhat fluidic here. In fact, it's an organic solvent. And if you know sort of what that means that if you go an organic solvent up under low pressure can turn into a gas phase very easily. In fact, in the old days, if you took a supercap and you went up over 10,000 feet, or you put them in an airplane, they'd actually swell up as this electrolyte turned into a gas under the lack of pressure in the upper atmosphere. Today, there's particular types of supercaps where they use an electrolyte that doesn't have that type of problem, and they can go up, you know, very, very far in the atmosphere and the low pressures and still operate just fine. So the commonality, though, between aging, which means that the whole device and the electrolyte is slowly diffusing and the parts just, you know, it's had too many cycles on it or whatever, you'll start to see the ESR slightly degrade over time. But if there's more of a catastrophic failure, like the electrolyte actually, you know, there's a pinhole leak or something like this, or the device is exposed to a lot of heat so that it's driving gas out of the system, then out of the supercap, then you will have the electrolyte dry up, and in which case the resistance is much, much faster change. Now we measure resistance here as equivalent series resistance, or ESR. And so on the left side, we see aging, we see the ESR going up slightly over time. It's dependent on temperature, operating voltage, you know, whether we've overstressed it and whether it sat in humidity for a long time or not. And then on dry up, this is like more of a particular failure where you have the supercap either overheating to a level where you're driving the electrolytic solution out of the part, damage to it, package sealant, the part wasn't built exactly right. These types of things can all be reason. But nonetheless, whatever the reason for the failure is, the way we detect it is, because remember, the failure isn't large. I mean, we're trying to detect ESRs on the order of 50 milliohms, and that is not an easy thing to do. Sorry, I got my slides screwed up here. 50 milliohms is not a very high impedance. If you run an amp through that, you get 50 millivolts, right, for a single amp. And so it seems like a lot of current to be able to check the ESR. So there's a couple of things we do. Obviously, we don't want to burn lots and lots of power checking our ESR, but ESR is important to check. And so what we do is we really do need to use a lot of current in order to do this, in order to get a big enough voltage we can sense. But in order to conserve the power, we want that pulse to be very fast. And so what we do is, in this case, our press to test, we use 120 microsecond pulse instead of using, 1 second pulse or something like that, where we're really generating a lot of power. We can use a very, very fast pulse, activate a particular switch. The switch turns on, it applies a load on the supercap. That instantaneous load is going to create a voltage offset that's directly proportional to the ESR. And using one of our comparators, we can see, oh, did it go above a particular level? So let's say we're looking for an ESR of 50 milliohms. If we put 2 amps into that, we're going to get about 100 millivolt offset. So we can set up one of our comparators at maybe 100 millivolts, maybe a little bit under that. And if we see a voltage that goes above that, when we jam on that, and what we're trying to do here is we're looking for a differential voltage. We're not just looking for a one wave, but it's the change in no pulse versus a pulse. And that's why you have the 2 different levels here that you're seeing. So we take a reference voltage, we apply the pulse is instantaneous, and the reference voltage here is this R2 by C2, and you can see we've got a big cap down here, so this thing doesn't move very fast. So that's our reference voltage. And on the other one, R3 to R4, there is no cap, and so we know that node is going to move a lot faster if we apply a current spike. And then to apply the current spike, we have a very low RDS on Q2 that we can switch and test that out and make it go really, really quick. So that's basically that circuit. Once again, lots of details online. Then we were talking about monitoring ripple current. This is AC current that's constantly going through a supercap. That ESR is there. It's not very high, but if you have a very strong AC level current whipping in and out of the supercap on a very high frequency basis, let's say an amp or 2, you can start to generate milliwatts of power consumption within the supercap itself. That will cause the temperature to rise. That will cause you to start to move along the curve of less lifespan on the supercap. And so we'd like to monitor that and say, well, we don't want to have a case where the supercap temperature is deviating too far from the ambient temperature. Otherwise, we know we have a problem, and maybe we need to slow something down, use a little less power, don't power, some electric motor as fast, or whatever the case is, in order to preserve the longevity of our supercap. And here's a bunch of stuff you can get off of the data sheet talking about the operating life of a supercap versus the temperature versus the charge voltage. And I'm not going to talk a huge amount about that today, but for every 10 degrees C increase in the ambient temperature, the lifetime of a supercap goes in half. We call that sort of like, the Arrhenius equation of supercaps. All right, and likewise, so if the ripple current is really high and the supercap itself is getting hot, well, that'll reduce the lifespan of that as well. So how do we monitor this? Well, in this case, our application engineer shows 2 temperature sensors. One is pretty much monitoring the ambient temperature, and then the other one is more attached directly to the supercap and monitoring the supercap. So we get both the ambient temperature. If that gets too high, we can get a warning. And we get the differential temperature, where if the differential between ambient and the supercap is more than 3 degrees C, we'll also get an alert. And so we can get 2 alerts off of them, both looking at the lifespan of the supercap. Very, very simple circuits. You can see, once again, you can integrate that. Now, what you're going to find with is in your application, I've given example after example, from charging circuits to cell balance monitoring to monitoring temperature. You can mix and match these circuits in most of our green packs. Most of our green packs have many more resources than what's pictured here. So this could be a feature of your chip for your supercap design. And you could also still add in the charger. You can still add in, the cell balancer and stuff like that, and create an entire solution. It's really up to your particular application. And of course, you can do all the timings and all the modes and blah, blah, blah. It's really all up to you. And then, so let's talk now about one of the last features that we want to discuss, and that is what happens when we do reverse voltage overcharging, say that 10 times real fast, short circuit protection. All right, but before we do that, do you guys want to go back to a video and see some supercaps blown up? Gotta have a vote. Mostly I'm trying to see if you're paying attention. Hey, there we got some supercap. All right, so let's go watch the rest of that video and see what happens.
Power's been out for a while.
Okay.
I'm going to look back at the video, and yeah, it's insanely hot. Oh, you can't even touch it. Well, there you go. What I'll do is now, maybe I'll do a smaller supercapacitor. And
yeah, now they're going to reverse polarity on the supercap.
Let's try a smaller one. What I've done here, this is a much smaller capacitor. It's the 2.7 volt, 0.5 farad capacitor. And what I've done is I've actually hooked up the polarity backwards. So I've got the positive on my power supply connected to the negative of the capacitor, and the negative of the capacitor connected to the positive of my power supply. So I think this one calls for some safety glasses. Actually, the first one called for some safety glasses too. So I'm going to record it right now, and I'm going to stand back.
This is what interns are for. Oh, here it goes. Oh, yeah.
Yes! In the aftermath, it smells absolutely horrible in here.
All right.
Probably a bad idea to do that in the house, but
yeah. So anyway, I'll get back to the presentation now. Where to go? There we go. All right. Okay. So you can clearly see that reverse voltaging a supercap is probably not a great idea. And so we probably want to discuss how you get around that. So that's why it can be important to maybe add diodes across each cell. Probably a good idea. The overcharging, a lot of times you might want to have a green pot monitor the voltage just with a standard comparator, and you might want to have a load switch be able to automatically disconnect, or one of our over voltage protection parts that we sell. We also sell those directly. And also overcurrent short circuit. There's all different types of things. You can use our load switches as overcurrent protection. We have some current monitoring kinds of things in some of our devices. We have short circuit protection in some of our load switches. You can put those in series and you'll protect your circuit in that manner as well. I'll give you a kind of a funny story that it reminded me of that video. When my dad had a medical company and my brothers, we worked there, one of the things we did was we would take a capacitor and would stick it into one of those power strips and turn the power strip on, but we'd turn the room lights off and make sure the power thing is in. So when my dad's employees would come in and they'd flick on the lights, we'd have these polyester caps or some of these really large caps that blow up, just very similar to that. That was back in the day when you didn't get turned into some state agency for this kind of thing, but it was kind of fun. So anyway, life has changed and we can't do that kind of thing anymore. But at any rate, so final wrap up. We went over active cell balancing, how to charge supercap, how to get the most out of your supercap in terms of the fixed output voltage, how to detect problems like aging, electrolyte dry up, how you monitor the temperature for lifespan, what you do about reverse voltage, how to avoid overcharging, short circuit protection in terms of using our load switches to handle all of those different types of conditions. So if anybody's got any questions, it'd be great to hear them now. Once again, I want to remind you that we've got seminars coming up in October and November, also on similar subject to this, as far as part of our 3-part series. We've got a lot of additional information at www.salego.com, applications, supercapacitor-interface that you see the link at the bottom of the screen here. We've got time for questions if anybody's got a question about Salego, our PAC chips, or IPS chips, or anything like that. We don't have any music to play, so if you don't, oh, we got one question. Thank you. Somebody, I bet it's like my mom or something like that. Oh, presentation says confidential. I don't know why it says confidential. So no, this presentation is not confidential, and we will make sure that it's that's removed and make that available for everybody. But thanks for pointing that out. Any other questions? I really like the easy ones like that. They're good, solid, nice ones. So I don't have any other open questions in front of me. Thank you guys all for joining me, and I hope you enjoyed it as much as I had given it to you. So you guys take care. Take care. Bye.